Sit back and enjoy 2 hours of fascinating facts you didn't know. Don't forget to leave a like and subscribe. Let's get started.
Tonight, we begin a journey through the immense Milky Way, the cosmic home that has accompanied humanity since the very beginning of our history. Among ancient stars, black holes, distant worlds, and mysteries that still challenge science, you will discover that our galaxy is far stranger and more fascinating than we ever imagined. Make yourself comfortable, look up at the sky with your imagination, and let this journey reveal the secrets that shine silently above us. Our galaxy may feel like a stable home, but it was built from the remains of others. Over billions of years, the Milky Way has absorbed smaller galaxies, pulling them in, tearing them apart, and scattering their stars into tidal streams that wrap around the galactic disk. One of these galaxies, the Sagittarius Dwarf Galaxy, is being torn apart right now. And far away in the night sky, Andromeda is slowly drawing closer. In about 4,500,000,000 years, the two great spiral galaxies will merge in a cosmic collision. The stars will almost never collide with one another, but the shapes of the galaxies will change forever, folding into a new form that is vast and peaceful. Not even galaxies last forever. They evolve, they collide, and they begin again. Some stars in the Milky Way are older than the Milky Way itself. Not every star in the Milky Way was born here. Some ancient halo stars, low in heavy elements and traveling along long, tilted orbits, appear to have formed even before the Milky Way fully took shape. Astronomers believe these stars may have originated in smaller primordial galaxies that merged with ours billions of years ago. Their chemical fingerprints contain almost no heavy elements, suggesting they were born shortly after the Big Bang. They move slowly, far above the galactic plane, like ancient spirits from a time before spiral galaxies, before order itself. In their light, we see a universe that was younger, wilder, and still learning to become what it is today. Our solar system orbits the center of the Milky Way at more than 514,000 miles per hour. That is more than 143 miles every second. Even so, it takes about 225 million years to complete just one orbit around the galaxy. This journey is called a galactic year. In Earth's timeline, we have completed only about 20 trips around the Milky Way since the solar system formed. When the first dinosaurs appeared, we were in a completely different part of the galaxy. The stars we see today were not always nearby, and they will not always remain. Everything is moving, silently, slowly, endlessly. While we sleep, Earth spins. The moon circles us, and the entire solar system travels through a galaxy that is itself in motion. The galaxy is still growing. Even though the Milky Way is ancient, it is not finished. Even now, it continues gathering material. Gas from intergalactic space, stars captured from dwarf galaxies, and streams of dark matter that feed its halo. It does not grow like a living creature, but like a gravitational structure that deepens over time. Some of this growth happens quietly through clouds that gradually add more material. Other times, it comes with disruption as satellite galaxies are torn apart and their stars are scattered across the sky. The galaxy you live in today is not the same one the dinosaurs once saw, and the one your distant descendants may one day know could be even larger, woven together from the ruins of 1,000 smaller worlds. We do not know exactly how many spiral arms the Milky Way has. It seems like something we should know. How many spiral arms extend outward from the center of our own galaxy? But from our position deep within the disk, it is difficult to see the entire structure. Clouds of dust hide the distant regions. The stars blur together. For decades, astronomers believed there were 4 main spiral arms. More recent observations have suggested there may be fewer, or that the arms twist and split in ways that are more complex than expected. Some fade into fragments. Others wrap around in unexpected ways. The Milky Way may not be a perfect pinwheel, but a living, layered swirl of stars shaped by forces we still do not fully understand. The Milky Way and Andromeda are on a collision course. Above the horizon, the Andromeda galaxy appears as a faint blur to the naked eye, a spiral galaxy much like our own, located more than 2 million light-years away. And yet, it is steadily moving toward us. In about 4,500,000,000 years, the Milky Way and Andromeda will collide. It will not be violent in the way you might imagine. The stars are far too widely separated to crash directly into one another. But their gravity will stretch and distort both galaxies into long, sweeping arcs. Tidal tails will curve outward. The black holes may spiral together. And after billions of years, the two galaxies will merge into a single, larger system. It will be a slow and graceful dance, the future of our cosmic home written across the stars. Some stars orbit backward. Most stars in the Milky Way orbit the galactic center in the same general direction. But not all of them follow the rules. Some stars, especially those in the outer halo, move in retrograde orbits, traveling in the opposite direction from the galaxy's main rotation. These stars most likely came from somewhere else, born in dwarf galaxies that were later absorbed. Their reversed motion is a quiet signature of their foreign origin. It is as though the galaxy carries ancient memories in its motion. Stories of long-forgotten mergers and cosmic encounters preserved not in light, but in the slow and patient turning of stars against the current. The Milky Way may have consumed dozens of dwarf galaxies. Over billions of years, the Milky Way has not grown alone. It has consumed. Small galaxies, faint companions, drifted too close, were captured by its gravity and slowly dismantled. Their stars are now part of our halo, our disk, or vast stellar streams. Astronomers have identified several of these mergers by studying the motions and chemical compositions of stars. One especially significant event, the Gaia-Enceladus merger, added countless stars and may have reshaped the galaxy's early structure. The Milky Way is not an untouched spiral. It is a composite built from silent collisions, woven together from the remains of many smaller worlds. The chemical composition of stars reveals where they came from. Every star carries a unique chemical fingerprint, a pattern of elements imprinted at its birth. By studying these signatures, astronomers can trace a star's history. Some stars are rich in heavy elements such as iron and calcium, suggesting they formed in dense, metal-rich regions. Others are made almost entirely of hydrogen and helium, born when the universe was still young. These differences allow scientists to group stars into families, uncover ancient mergers, and reconstruct the hidden history of the Milky Way's formation. In this way, chemistry becomes a kind of time machine that allows us to read a star's past like a line of ancient poetry written in light. The sky is filled with stellar streams from shattered galaxies. Across the heavens, thin ribbons of stars stretch in graceful arcs and curves, barely visible but unmistakable when mapped with precision. These are stellar streams, the remains of smaller galaxies that wandered too close to the Milky Way and were torn apart. As they orbit, their stars are scattered through space by tidal forces, creating long and delicate trails that trace their ancient paths. Some wrap around the galaxy like ghostly halos. Others plunge toward the galactic core. These streams are evidence of past collisions, silent mergers that built the Milky Way over billions of years. Like a tree, the galaxy carries the rings of its past in every thread of light. Milky Way is warped. Our galaxy is not flat like a perfect spiral. Its disk bends upward on one side and downward on the other, creating a graceful wave across the stars. This subtle distortion remained invisible until radio telescopes mapped the hydrogen gas extending far beyond the visible starlight. Astronomers believe the warp may be caused by satellite galaxies gently tugging at the edges of the Milky Way or by clumps of dark matter bending its structure from below. Like ripples across a giant spinning sheet, the warp reveals that not even galaxies remain completely still. Over time, they bend, flex, and change shape in response to invisible forces. From a distance, the Milky Way might appear to be slowly dancing through space. You can see only about 0.00003% of the Milky Way with the naked eye. Under a clear, dark sky, far from cities and streetlights, you might see a few thousand stars. To the human eye, that seems like an ocean of light, but it is only a drop. The Milky Way contains more than 100 billion stars. Most are hidden from view. Some lie behind dense curtains of dust. Others are too faint or too distant for our vision to reach. The pale band of the Milky Way stretching across the sky on moonless nights is only the faintest whisper of the whole. We live surrounded by a colossal river of starlight, and yet almost all of it remains invisible to us, far too vast to fully understand from within. Stars orbit the galaxy at different speeds. Unlike the planets in a solar system, which follow orderly paths around their star, the stars of the Milky Way move with much greater freedom. Some race ahead in the inner regions, while others drift more slowly through the outer edges. This difference in speed is the reason spiral arms form. They are not solid structures, but patterns similar to slow-moving traffic jams of stars and gas traveling through space. As these density waves pass by, they trigger the birth of new stars, lighting up the spiral arms with blue and white curls. Our own sun is part of this great whirlpool, moving in and out of these patterns over time. The galaxy is not a clock. It is a current, and we are floating within it. The galaxy is held together by something we cannot see. By all logic, the Milky Way should not exist. Based on what we can measure, the stars, dust, and gas along the galaxy's outer edges are rotating far too quickly. They should be flung into space, scattered like leaves in a storm. And yet, they remain. The answer is dark matter. This mysterious substance does not shine, reflect, or emit light, but it exerts gravity, and there is so much of it that it outweighs all the visible matter in the galaxy many times over. We do not know what dark matter is, but we do know that without it, the Milky Way would fall apart. It is the invisible framework that holds everything in place. There is a supermassive black hole at the core. At the very center of the Milky Way lies a massive black hole, a singular point of gravity known as Sagittarius A star. It has more than 4 million times the mass of the Sun, yet it occupies a region smaller than Mercury's orbit. We cannot see it directly, but we have watched nearby stars race around it at tremendous speeds, tracing invisible loops through the void. At times, gas and dust fall inward and glow in X-rays as they spiral toward the event horizon. For now, Sagittarius A star is quiet. But long ago, it may have blazed like a quasar, lighting up the galaxy from within. It is the silent conductor at the heart of the Milky Way, drawing stars into a slow and tireless dance. Milky Way has a peanut-shaped bulge. When astronomers mapped the center of the galaxy, they discovered something unexpected. The central bulge is not a smooth, round sphere of stars, but a three-dimensional peanut shape. Seen from the side, it swells in the middle and narrows at the ends like a rotating hourglass made of stars. This unusual geometry most likely formed from the galaxy's central bar, a dense band of stars that slowly rotates, bending and bulging upward over time. These inner structures have been sculpted by gravity, billions of years of motion, and the accumulated rhythm of stellar orbits. We live in a spiral galaxy, but its heart is filled with complexity. It is not flat or simple, but intricate and alive. Stellar nurseries shape the spiral arms. The Milky Way's spiral arms are not made simply of stars. They are woven from the birthplaces of stars. Giant clouds of hydrogen, dust, and molecules drift through the galaxy. And when these clouds pass through the spiral arms, they are compressed and ignite with newborn suns. These regions are called stellar nurseries, chaotic, brilliant, and full of motion. Ultraviolet light from the young stars illuminates the clouds, painting the spiral arms in radiant shades of blue and silver. These bursts of creation trace the spiral pattern, lighting up the galaxy's curves with silent fire. Every star, including the Sun, was born in one of these cloudy cradles long ago. The Milky Way is surrounded by a vast halo. Beyond the flat spiral disk lies something far more diffuse, a spherical halo that surrounds the entire galaxy. It contains ancient stars, globular clusters, and enormous amounts of dark matter. Although it is almost invisible, this halo may contain most of the Milky Way's mass. Its stars are spread across immense distances, orbiting in long, slow arcs that rarely cross the disk. The halo also preserves the remains of ancient galactic mergers, streams, and shells of stars torn from smaller galaxies and left behind like cosmic fossils. It is the galaxy's outer memory, quiet and faint, yet still in motion, still shaping what the Milky Way is becoming. It contains more than 150 globular clusters. Globular clusters are among the oldest objects in the galaxy. They are compact spheres made up of hundreds of thousands of tightly bound stars. They orbit the galactic center within the halo like moths circling a distant flame. These clusters are remarkably stable, some more than 12 billion years old, and many contain stars that are older than the Milky Way itself. Their stars are poor in heavy elements, meaning they formed before the universe had enough time to create many of the heavier elements. They serve as time capsules, preserving clues about how the galaxy formed, what it consumed, and what conditions were like in the early universe. These quiet golden spheres drift patiently above and below the galactic plane, glowing in the darkness. Runaway stars are hurled from the core. Most stars travel peacefully through the galaxy, but a few are flung outward at astonishing speeds, fast enough to escape the Milky Way entirely. These are called hypervelocity stars. Some are the remnants of binary star systems disrupted by the supermassive black hole at the center of the galaxy. One star falls inward and disappears. The other is launched outward, hurled into the darkness at more than 621,000 miles per hour. These runaway stars travel alone, far beyond the galactic plane, like brilliant comets with no return. They remind us that even in a galaxy held together by gravity, there are moments of violent release, silent ejections that send stars flying into intergalactic space. Star formation is slowing down. Long ago, the Milky Way was far more active, filled with fresh stars born from collapsing dense clouds. But in more recent ages, the pace has slowed. There is still gas available, but much of it is too spread out, too warm, or trapped in forms that resist collapse. The galaxy has not finished making stars, but it is settling down. Astronomers estimate that star formation reached its peak billions of years ago and has been declining ever since. That does not mean the end is near. It simply means we live in a quieter chapter. A mature spiral glowing gently through its middle age, still creating stars, but no longer in a hurry. Some stars formed before the Milky Way had a disk. The disk, the broad, flat spiral we think of as the Milky Way, formed gradually over time. But some of the stars in our galaxy are older than the disk itself. These ancient stars are found mainly in the halo or the thick disk, and they formed while the galaxy was still coming together, a loose cloud of stars, gas, and dark matter slowly collapsing inward. By studying their composition and motion, astronomers can look back to a time before structure, before spiral arms. These stars are the galaxy's oldest inhabitants, silent witnesses to its birth and to the long, gradual shaping of what we now call home. A galactic year lasts between 225 million and 250 million Earth years. As the Sun orbits the center of the Milky Way, it completes one full revolution every few hundred million years. This is called a galactic year, a vast cycle of motion that makes all of our calendars seem insignificant. During the time it takes the Sun to complete one orbit around the galaxy, continents drift, species rise and disappear, and entire eras unfold. Scientists believe we are currently about halfway through one of these orbits. The last time the solar system was in this part of its journey, the supercontinent Pangaea had only just begun to break apart, and the dinosaurs had not yet appeared. A galactic year is the slow heartbeat of cosmic time. The Sun has completed fewer than 25 galactic orbits. Throughout its 4,600,000,000 years of existence, the Sun has circled the Milky Way only about 20 times. That is fewer than you might expect, considering its incredible speed of nearly 516,000 miles per hour. But the galaxy is so vast, and the Sun's path is so long, that each orbit takes hundreds of millions of years. We often think of stars as ancient and motionless. But on a galactic scale, our solar system is still young, a newcomer in a city of older and more well-traveled suns. We are part of the galaxy's motion, but we are still at the beginning of its long and winding story. The Milky Way's rotation defies Newton's predictions. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, just as the outer planets move more slowly around the Sun. Yet in the Milky Way, the stars in the outer regions orbit almost as quickly as those near the center. This defies classical expectations. Astronomers believe the reason is dark matter, an invisible and unknown form of mass that surrounds the galaxy in a vast halo. Without dark matter, the galaxy would not remain intact. With it, the mathematics works. The Milky Way rotates like a solid wheel, not because we fully understand it, but because something unseen holds it together. The galaxy contains enormous molecular clouds. Scattered throughout the Milky Way are vast, dark clouds of cold gas, the raw material from which stars are born. These molecular clouds, made mostly of hydrogen molecules with traces of dust, can stretch across hundreds of light years. Deep within their cold, dense interiors, gravity begins gathering material, forming clumps that collapse into new stars and planets. Some of these clouds are so large and so cold that they block visible light completely, appearing as black patches against the star-filled sky. They are the wombs of the galaxy, quiet and hidden places where the future begins in silence, concealed behind curtains of shadow and gas. Supernovas stir the galaxy like storms. When massive stars reach the end of their lives, they explode in catastrophic supernovas. These events are so powerful that they can briefly outshine entire galaxies. These explosions do not just end lives, they create them. The shock waves from supernovas race through interstellar space, compressing nearby clouds and triggering new waves of star formation. They enrich the surrounding space with heavy elements such as iron and gold, forged in the heart of the dying star. In this way, supernovas act like storms within the galactic ecosystem, stirring, enriching, and reshaping everything around them. They are the galaxy's moments of chaos, destructive, radiant, and essential. Dust hides vast regions of star formation. The Milky Way is filled with light that we cannot see. Interstellar dust, made of microscopic grains of carbon, silicates, and ice, weaves its way through the galaxy in clouds and tendrils. In visible light, it obscures enormous regions of space, hiding entire stars and nebulas. But behind this veil, star formation continues. Infrared telescopes can see through the dust, revealing dazzling stellar nurseries filled with newborn suns. What appears to be darkness is often a cradle. Dust, even while it hides, is part of the process. It absorbs energy, helps cool the gas, and protects the delicate stages of stellar birth. What looks empty is often the beginning of something brilliant. There are starless gas clouds drifting through the galaxy. Not every gas cloud becomes a star. Throughout the Milky Way, astronomers have found massive cold clouds that appear ready to collapse, yet remain dark and inactive. Some are too diffuse. Others may be stabilized by magnetic fields or internal turbulence. These starless clouds drift through the galaxy like quiet possibilities, rich in molecular hydrogen but untouched by nuclear fusion. One day they may ignite, or they may drift until they are torn apart by outside forces, with their gas recycled into other regions. Within these clouds, the galaxy seems to hold its breath, perhaps waiting for just the right push to ignite something new. Milky Way recycles matter through generations. Stars are not permanent. They live, they burn, and they die. And when they die, they return their material to the galaxy. Supernovas scatter heavy elements. Red giants shed their outer layers. Planetary nebulas drift into space. This enriched material joins the interstellar medium, where it cools, condenses, and eventually forms new stars, planets, and even life. Every atom in your body has passed through this cycle, born inside a star, scattered across space, and gathered together into a new form. The Milky Way is not a static stage, but a vast engine of renewal. It breathes with the rhythm of its stars, creating, unraveling, and beginning again. Metal-poor stars preserve clues about the early universe. In astronomy, metals are not just iron or gold. They are any elements heavier than helium. The first stars in the universe contained almost no metals because they formed before earlier generations of stars had the chance to forge and scatter them. Today, astronomers search for metal-poor stars in the Milky Way's halo. These faint and ancient stars preserve the chemical conditions of a distant age. By analyzing their composition, we look back into the primordial past, to the era after the Big Bang, before galaxies had matured, and before our own galaxy had taken its full shape. They are fossils made of light. Some stars wander far from where they were born. A star's birthplace does not always determine its destiny. Over time, many stars drift away from their natal clouds, pushed by gravitational interactions, orbital resonance, or the slow pull of the spiral arms. Some stars are ejected at tremendous speeds, hurled across the disk or out into the halo. Others gradually migrate, shifting their orbits inward or outward as they circle the galaxy. Even our sun is no longer where it began. Tracing the paths of stars reveals a Milky Way that is anything but static, a living galaxy filled with motion, exchange, and quiet migration. A star's home may be only temporary. The galaxy's habitable zone may stretch across tens of thousands of light-years. Just as Earth orbits within the Sun's habitable zone, not too hot and not too cold for life, the Milky Way may have its own galactic habitable zone. Scientists believe this region lies between the dangerous inner core, filled with radiation and gravitational chaos, and the sparse, metal-poor outer edges, where planets may be more difficult to form. Somewhere in between lies a broad band where conditions are stable, stellar density is moderate, and elements such as carbon, oxygen, and iron are abundant. Earth lies within this zone, a quiet orbit inside a vast cosmic whirlpool where life may not be the only thing to find a home. Spiral arms are not fixed structures. The Milky Way's spiral arms may appear to be permanent features, great lanes stretching across the galaxy's disk, but they are not made of fixed stars. Instead, they are patterns, density waves that slowly move through the disk, compressing gas and triggering new stars as they pass. Stars drift into these arms, shine there for a while, and then drift back out again. The spiral pattern moves at a different speed than the stars themselves, much like a traffic jam moving along a highway. From a distance, it looks like shape and order. From within, it is a changing pattern of motion sustained by gravity and time, never still, always flowing. The Milky Way hums with cosmic radiation. Beyond visible light, the galaxy glows with more mysterious forms of energy. Cosmic rays, high-energy particles born in supernovas and distant galaxies, stream through space and pass through your body every second. X-rays and gamma rays shine from dying stars and black holes. Radio waves drift from gas clouds, pulsars, and the cold breath of hydrogen. These invisible signals reveal what light cannot: the violence, magnetism, and ancient fires that still flicker within the bones of the galaxy. When you look up at the night sky, you are seeing only a narrow slice of the Milky Way's true spectrum. Beneath the stars, the galaxy hums softly in many colors, across many frequencies, like a symphony hidden within the darkness. There is a giant gamma-ray bubble above and below the core. Stretching tens of thousands of light-years above and below the galactic center are two enormous ghostly lobes of high-energy light known as the Fermi bubbles, discovered only recently. They glow in gamma rays and extend like twin balloons from the heart of the Milky Way. No one is completely certain what created them. They may be the remains of an ancient outburst from the central black hole or the signature of an intense burst of star formation that once blazed within the core. Either way, these immense structures float silently above the galaxy, invisible to human eyes. They remind us that the Milky Way has a past we cannot fully see, echoes of violence wrapped in a glowing veil high above the stars we know. We live in a minor spur between the major spiral arms. Our solar system is not located within one of the Milky Way's great spiral arms. Instead, we occupy a smaller structure known as the Orion Spur, a relatively quiet lane of stars situated between the larger Sagittarius and Perseus arms. It is not especially dense or especially active, but perhaps that is why we are here. In the calm between the galaxy's great highways, massive supernovas are less common and radiation storms are less frequent. This peaceful corner may have given life on Earth the time it needed to emerge and evolve. From the outside, the galaxy appears dramatic and radiant. But within this quiet spur, we found enough peace for complexity to flourish. The Milky Way has a barred center. When astronomers observe the galactic core in infrared light, they do not see a perfect circle. Instead, they see a thick, elongated bar of stars stretching across the middle like a brilliant bridge. This bar rotates slowly, and its gravitational pull shapes the inner spiral arms. Bars like this are common in spiral galaxies. They form when stars in the disk begin drifting inward and gathering along a central axis. Over time, The bar becomes a stable structure that stirs the gas, triggers new stars, and feeds material to the black hole at the galaxy's center. It is not just a shape, but a dynamic engine that sculpts the heart of the galaxy from within. It is part of a larger structure called the local group. The Milky Way does not exist in isolation. It belongs to a collection of more than 50 galaxies known as the local group, a small cluster drifting together through space. Its two largest members are the Milky Way and Andromeda, each with its own family of satellite galaxies. Scattered around them are smaller dwarf galaxies, faint elliptical galaxies, and star-poor galaxies made almost entirely of dark matter. The local group spans more than 10 million light-years and is held together not only by proximity, but also by gravity. We are part of this family, quiet, widely separated, yet still connected by the invisible threads of shared motion and mutual attraction. Galaxies of the local group are gravitationally bound. Despite the vast distances between them, the galaxies of the local group are not moving apart. In fact, many of them are slowly moving toward one another. Gravity holds them in a kind of slow-motion dance, bending their paths over millions of years. Some of the smaller galaxies orbit the Milky Way like moons, circling, falling, and dissolving into streams. Others drift independently but remain bound, trapped within a network of shared motion. Over time, this group may become more compact. Galaxies may merge, fade away, or be absorbed. It is not a static arrangement, but a gentle gathering of cosmic islands, a family drawn together by time, inertia, and the long reach of gravity. Galaxy's disk has both a thick component and a thin component. From a distance, the Milky Way's disk appears flat, but up close, it is layered. The thin disk is where we live, a broad, dense plain filled with young stars, open clusters, and star-forming gas. Above and below it lies the thick disk, which is older, more swollen, and more diffuse. Stars in the thick disk tend to be older and contain fewer heavy elements. They move in more inclined and elliptical orbits, suggesting that they formed under different conditions or were stirred up by early galactic collisions. The galaxy's disk is not uniform. It is textured, layered, and shaped by time, like sediment settled at the bottom of a cosmic ocean. Galaxy's magnetic field runs through the disk. Although it is invisible to the eye, the Milky Way is threaded with a vast magnetic field that stretches across the disk, rises into the halo, and weaves through interstellar space. This field is weak by Earth standards, but across galactic distances, it influences how cosmic rays travel, how gas clouds collapse, and how matter flows through space. It aligns with the spiral arms, forms arches above the galactic plane, and twists into loops that resist simple explanation. Studying it requires radio telescopes and careful analysis, but its presence is unmistakable. The Milky Way does not only shine with light, it breathes with magnetism, a subtle pulse running through its bones. The interstellar medium is filled with invisible structures. Between the stars, there is more than empty space. The interstellar medium, a thin mixture of gas, dust, and plasma, winds through the Milky Way like a mist. To the naked eye, it is almost invisible. But when observed with radio and infrared telescopes, it reveals astonishing complexity. It forms filaments, bubbles, shock waves, and cold, dense clouds where stars are born. Supernovas carve vast cavities into it. Stellar winds shape it into forms that curl across light years. The space between the stars is not a vacuum, but a changing network of matter and magnetism, the silent fabric from which galaxies evolve and from which life eventually begins. Cosmic rays from the galaxy constantly pass through us. Every second, high-energy particles, mostly protons and atomic nuclei, stream through your body after being launched long ago by exploding stars. These are cosmic rays, and they are everywhere. They travel close to the speed of light, curving through magnetic fields, bouncing through clouds, and occasionally colliding with atoms in Earth's atmosphere, where they create showers of secondary particles. Most of the time, we do not notice them, but they carry stories from across the galaxy. Evidence of ancient supernovas, traces of distant acceleration, and messages from the violent hearts of stars. Even while you rest, the galaxy is whispering through particles, silently, in rays without light. The galaxy is not symmetrical. Although many diagrams show it as a clean and uniform spiral, the Milky Way is not perfectly balanced. One side of the disk appears thicker. Some spiral arms are brighter, longer, or more curved than others. The warp in the outer disk is uneven. Even the number of stars in each hemisphere is slightly different. These asymmetries may be caused by gravitational encounters, past mergers, or the influence of dark matter. They remind us that galaxies, like living beings, carry traces of their histories in their shapes, scars from collisions, wrinkles formed by time, and peculiarities created by uneven growth that give them character and depth. The oldest known star may live in our halo. Far above the galactic plane, drifting through the halo, astronomers discovered a star that may be nearly as old as the universe itself. It contains almost no heavy elements, a signature of stars born shortly after the Big Bang, before generations of supernovas enriched the cosmos. It probably formed more than 13 billion years ago, long before the Milky Way was fully assembled. It now burns quietly with a soft red glow, low in mass but rich in history. It is not merely a star. It is a time capsule, a living relic from the earliest dawn of the universe. The center of the galaxy rotates faster than the outer regions. In the inner regions of the Milky Way, stars orbit the center much faster than those farther away. Near the core, the gravitational pull is stronger because of the enormous concentration of stars, dust, and the supermassive black hole Sagittarius A star. This causes stars to follow tighter and faster orbits, completing revolutions in only a few million years. In the galactic suburbs, where our Sun is located, stars orbit more slowly and take hundreds of millions of years to complete a revolution. This uneven rotation creates twisting patterns, stretches the spiral arms, and prevents the disk from behaving like a solid structure. The galaxy moves like a great wheel, but one whose outer edge falls behind its core. The spiral arms are shaped by density waves. The Milky Way's spiral arms are not fixed paths made of stars. They are patterns formed by waves of greater density moving through the galactic disk. As gas and dust pass through these waves, they are compressed, triggering star formation and lighting up the arms with young, brilliant stars. Over time, these stars move out of the wave while new ones form behind them, creating a self-sustaining illusion of structure. Like ripples in a pond or traffic compressing on a highway, the arms are dynamic and always in motion. From a distance, they appear still. From within, they are a dance of matter and rhythm, shaped by gravity and time. Stars are born from collapsing cold gas. In the dark arms of the Milky Way, star formation begins in silence. Massive clouds of molecular hydrogen, sometimes hundreds of light years across, drift through space, cooled to only a few degrees above absolute zero. Inside these clouds, gravity slowly takes control. Small regions become denser and begin collapsing under their own weight. As the gas falls inward, it heats up, spins, and flattens, forming a protostar at the center. Over time, pressure and temperature rise until nuclear fusion ignites and a new star is born. From the coldest shadows come the brightest lights, gently shaped by the silent force of gravity. Star clusters can dissolve into the galactic field. Many stars are not born alone, but in groups, tightly packed clusters formed from the same collapsing cloud of gas. These clusters, held together by mutual gravity, drift together for millions or even billions of years. But over time, they begin to scatter. Tidal forces from the Milky Way's mass, close encounters with other stars, and internal dynamics work to pull the clusters apart. Stars break away one by one until the cluster fades into the galaxy's general stellar field. Even our Sun was born in a star cluster long ago. Its siblings are now scattered, dimmed, or lost in the haze of distance. Galaxy contains ancient hypermetal-poor stars. Among the rarest and most valuable objects in the Milky Way are hypermetal-poor stars, stars whose atmospheres contain almost no elements heavier than helium. Some of them contain less than 1/10,000th of the iron found in the Sun. These stars are believed to be among the first born after the very first supernovas, carrying only faint traces of enrichment from a universe that was still taking shape. They are incredibly ancient, incredibly pure, and scattered throughout the halo like distant lanterns from the dawn of time. Each one is a kind of relic, a glowing signature held together by gravity from an almost forgotten age. Planetary systems form throughout the Milky Way. Planets are not a rare feature of the cosmos. They are a natural consequence of star formation. As a new star ignites, it is surrounded by a rotating disk of leftover gas and dust. Within this disk, particles stick together, gather mass, and grow into worlds. Across the Milky Way, planetary systems are common. Some are vast, with gas giants and frozen moons. Others are compact, with rocky planets orbiting very close to faint stars. Some may resemble our own, while others completely defy our expectations. The galaxy is not only filled with stars, it is filled with systems, solar families, each with its own unique balance, orbit, and potential. Earth lies near the Curiosities radius. In the Milky Way, the spiral arms rotate at a different speed from the individual stars, behaving like a moving pattern rather than a solid structure. However, there is a special distance from the center called the Curiosities radius, where the average speed of the stars matches the rotational speed of the spiral arms themselves. Earth's sun orbits near this boundary. This gentle alignment in motion may help us avoid frequent crossings of the spiral arms, regions with greater stellar density, more supernovas, and stronger gravitational disturbances. We may live in a more stable neighborhood of the galaxy, protected not by walls, but by resonance. Sun moves up and down through the galactic plane. As it orbits the Milky Way, the Sun does not follow a perfectly flat path. Instead, it moves in a gentle wave, drifting above and below the galactic plane like a cork in slow motion, rising and falling over tens of millions of years. This vertical oscillation is caused by the gravitational pull of the galaxy's mass, which draws the solar system inward and releases it as it moves. Some researchers have even wondered whether this motion could influence extinction cycles on Earth, although the evidence remains unclear. Even so, it is a reminder that even along its steady path around the center, the Sun does not simply glide. It gently sways through space. We do not know what dark matter is, but we know it is there. Dark matter makes up most of the Milky Way's mass, even though it has never been directly observed. It does not emit or absorb light. It passes through ordinary matter as though it were not there. But its gravitational effects are unmistakable. It holds the galaxy together, explains the unexpected rotational speeds of stars, and shapes the formation of cosmic structures on the largest scales. Without it, the Milky Way would fall apart. Astronomers do not detect it by seeing it, but by observing how it moves other things. It is the hidden framework of the galaxy, invisible, silent, and still one of the greatest mysteries in science. There is more mass outside the disk than inside it. Most of the Milky Way's visible stars are located within its flat, luminous disk, but most of its mass lies elsewhere. The galaxy is surrounded by an enormous halo of dark matter that extends far beyond the most distant stars. This halo holds the galaxy together and outweighs the disk by a wide margin. It is sparsely populated by ancient stars and globular clusters, but its true volume cannot be seen. When we think of the Milky Way, we imagine its spiral arms and star-filled plane. But that is only the glowing surface. The mass that defines the galaxy, its gravity, motion, and reach, is mostly hidden, surrounding everything like a silent cloak. The core of the Milky Way may once have shone like a quasar. Today, the heart of our galaxy appears calm, but there is evidence that it was once dramatically more active. The presence of enormous gamma-ray structures, such as the Fermi bubbles, along with traces of high-energy light reflected by surrounding clouds, suggests that the supermassive black hole at the center may once have shone like a quasar, a brilliant and violent beacon powered by matter falling into it. Quasars are among the brightest objects in the universe and can outshine entire galaxies. If the Milky Way once blazed in this way, it would have looked dramatically different, a spiral wrapped around a heart of dazzling light. That time has passed, but the echoes remain. The structure of the galaxy changes over billions of years. Galaxies may appear eternal, but they are always evolving. Spiral arms shift. Bars form and dissolve. Gas flows inward and outward. Stars are born and die, leaving behind a changing population. Even the shape of the Milky Way's disk, warped, rippling, and uneven, is slowly changing. Encounters with dwarf galaxies and dark matter can bend or twist its structure. Over billions of years, the galaxy's silhouette has shifted like a drifting cloud. The Milky Way of today is not what it once was, nor what it will become. Its beauty does not lie in permanence, but in silent transformation. Gravitational waves travel through the galaxy from distant mergers. Across the universe, massive objects collide. Black holes spiral together until they merge, neutron stars crash into one another, and entire galaxies combine. These events send out gravitational waves, ripples in the fabric of space-time itself. Although faint, some of these waves pass through the Milky Way, distorting space by incredibly small amounts as they travel. They are extremely difficult to detect, but observatories, such as the Laser Interferometer, Gravitational Wave Observatory, and Virgo, have already captured several. New experiments aim to detect the background hum of gravitational waves that fills the cosmos. Even now, while you rest, space itself is shifting. Not enough for you to feel it, but enough to tell us that somewhere far away, the universe is changing. Some stars orbit along elongated and tilted paths. Not every star moves in a clean circle around the galactic center. Some follow highly stretched ellipses, with paths that rise far above and fall far below the disk, tilted at unusual angles relative to the main plane. These stars likely have different origins, relics of dwarf galaxies consumed by the Milky Way, or survivors of ancient gravitational upheavals. Their orbits are clues, three-dimensional maps of the galaxy's chaotic past. By tracking their motion, astronomers reconstruct the invisible architecture of the Milky Way's mass and memory. These stars drift like messengers from disrupted systems, tilted, stretched, but still bound to the whole. Milky Way emits neutrinos that we can barely detect. Every second, trillions of neutrinos pass directly through your body from the stars. These ghostly particles are produced in nuclear reactions within the sun, in supernovas, and when cosmic rays collide with atoms in space. The Milky Way is filled with them. Yet they are so light and interact so weakly that they pass through almost anything without leaving a trace. Special observatories buried deep underground or beneath the ice attempt to capture only a few of them, brief flashes of light produced by a rare collision. Neutrinos carry information from places we cannot see: stellar cores, collapsing giants, and the unseen energy of the galaxy. They are the whispers of cosmic fire. Interstellar space is not empty. It is a turbulent sea. Between the stars, space is neither smooth nor still. The interstellar medium, made of thin clouds of gas and dust, is stirred by shock waves, magnetic fields, and the movement of stars. Temperatures can vary enormously. Streams of material collide, mix, and break apart. Clouds stretch, fold, and churn. On a large scale, this creates a kind of turbulence, like a slow-motion ocean swirling through the disk. Star formation, cosmic rays, and even galactic evolution are affected by this restless sea. What appears from a distance to be calm starlight is, up close, a dynamic and rippling fabric shaped by invisible winds and ancient energy. The galactic halo may contain rogue planets. Planets are not always bound to stars. Some form normally and are later ejected from their systems. Others may never have had a star at all. These are rogue planets, worlds drifting through the galaxy, cold, dark, and alone. Although they are difficult to detect, studies suggest that there may be billions of them in the Milky Way, some even in the outer halo, where stars are few and widely separated. Without light or warmth, they float unseen. Heated only by their own internal energy, they are the orphans of the galaxy, planetary wanderers following long and lonely paths through the darkness between the stars. Magnetic fields shape the flow of cosmic dust. Interstellar dust, made of tiny grains of carbon and silicate, moves not only under the influence of gravity, but also under the influence of the galaxy's magnetic field. These fields run through the Milky Way like invisible currents, guiding the motion of charged particles and influencing how gas and dust align. In some regions, dust grains spin rapidly, producing a faint microwave glow. In others, they align with magnetic field lines, polarizing the starlight that passes through them. Understanding these effects helps astronomers trace the structure of the magnetic field and even remove its influence from studies of the cosmic background. Dust is not passive. It dances to a magnetic rhythm, following hidden patterns in the darkness. Some stars are enriched by neutron-star collisions. When two neutron stars spiral together and collide, they create one of the most violent events in the universe, a kilonova. In this brief and dazzling explosion, enormous amounts of heavy elements are forged, including gold, platinum, uranium, and more. These materials are thrown into space, mixing with gas and eventually becoming part of new stars. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched with elements that could only have come from such collisions. They are not merely glowing bodies, but guardians of ancient cataclysms, burning with the remnants of stellar debris and cosmic alchemy. Milky Way may have a hidden bar inside another bar. At the heart of the galaxy lies a bar of stars, an elongated bridge of light crossing the central bulge. But deep within that bar, astronomers have found evidence of another, smaller bar, tilted at a different angle and rotating independently. This inner structure is difficult to observe directly because it is obscured by dust and distance, but its gravitational influence appears in the motion of nearby stars and gas. Bars like this can help channel material toward the supermassive black hole, feeding it and shaping the dynamics of the core. The center of the Milky Way is not a simple structure. It is a layered and shifting maze of light and motion. Gas inflows feed the galaxy from the cosmic web. The Milky Way is not a closed system. It draws in fresh gas from intergalactic space through long, faint streams flowing along the vast cosmic web. These inflows provide the raw material for new stars, replenishing what the galaxy loses over time. Some of the gas arrives in the form of cold filaments that slip quietly into the disk. Other streams fall in at higher temperatures, heated by shock waves and glowing in ultraviolet or X-ray light. These invisible rivers sustain the growth and evolution of the galaxy, linking it to the larger universe around it. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter woven since the early universe. Bubbles of hot gas form chimneys out of the disk. When groups of massive stars explode as supernovas, they create enormous cavities in interstellar space. These cavities can merge into superbubbles, vast pockets of hot gas that push upward through the galactic disk and vent into the halo. The result is a kind of chimney, a channel through which energy, gas, and magnetic fields escape from the plane of the galaxy. These chimneys regulate pressure in the interstellar medium, redistribute heavy elements, and help shape the structure of the halo. In this way, the galaxy does not only breathe within the disk, but also through towering columns that carry its energy upward and outward into the darkness. The galaxy glows in X-rays from old stars and black holes. Although the Milky Way appears calm in visible light, it shines intensely at other wavelengths. X-rays pour from its core, collapsed stars, and the edges of black holes. White dwarfs and neutron stars in binary systems can pull material from their companions, heating it to millions of degrees. Hot gas in the halo also emits faint X-rays, revealing the galaxy's larger skeleton. We cannot see this high-energy light with our eyes, but telescopes such as Chandra and XMM Newton reveal a very different portrait of the galaxy. Not a peaceful spiral, but a realm of extreme temperatures, compact remnants, and hidden radiation. Pulsars act as cosmic clocks throughout the Milky Way. When a massive star dies and collapses into a neutron star, it may be left spinning rapidly and with remarkable precision, sending beams of radiation sweeping through space. These objects are pulsars, and some rotate hundreds of times per second, producing pulses in regular and measurable rhythms. They are so consistent that astronomers use them as cosmic timekeepers, tracking their signals to measure distances, test gravity, and even search for gravitational waves. Across the Milky Way, pulsars flash silently, remnants of death, but also beacons of astonishing order. They do not measure time in minutes or days, but across entire ages, ticking steadily in the silence between the stars. Radio waves map the hidden structure of the galaxy. Much of the Milky Way is invisible in visible light, concealed by dust, distance, or faintness. Radio waves, however, can pass through these barriers and reveal structures that would otherwise remain unseen. They trace cold hydrogen gas, outline magnetic fields, and highlight emissions from pulsars, supernova remnants, and even distant quasars beyond the galaxy. Using arrays of radio telescopes, astronomers have mapped the spiral arms, measured the warp of the disk, and discovered star-forming regions hidden by darkness. Where visible light is blocked, radio surveys allow us to see. The galaxy speaks in a language we cannot hear, but science has learned to translate it into shapes and shadows. The Sun was probably born in a star cluster. Stars rarely form in isolation. They are usually born in groups, within star clusters created from the same collapsing cloud of gas and dust. Our Sun was almost certainly one of them. Long ago, it shared space with hundreds, perhaps thousands, of sibling stars, all born in the same cradle. Over time, gravitational tides, passing stars, and the movement of the galaxy scattered the cluster. Most of the Sun's siblings drifted far away, thrown into different orbits and carrying pieces of our shared past with them. Some may still shine nearby, hidden among the stars like a lost family in a sea of light. Sun's sibling stars are scattered throughout the galaxy. Although the Sun's birth cluster dissolved long ago, astronomers are searching for its lost siblings, stars that share its age, motion, and chemical fingerprint. Using large surveys such as Gaia and spectroscopic databases, researchers hope to identify these long-lost relatives. A few candidates have emerged, stars that may have shared our origin and formed from the same enriched cloud of gas. If they are found, they could reveal details about the conditions in which the Sun and the early solar system were born. Our place in the galaxy is not entirely solitary. Somewhere out there, the Sun's ancient relatives may still be shining. The galactic disk wobbles as it rotates. The Milky Way's disk is not perfectly flat. It gently wobbles, rippling like an unbalanced spinning plate. This warp is most visible in the outer regions, where the disk bends upward on one side and downward on the other. It may be caused by the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries. The wobble rotates slowly, like a great wave moving through the stars. From Earth, we do not feel it. But from a distance, the Milky Way is not a pristine spiral. It is a breathing, rippling sheet of stars, gently bending as it turns. Galactic tides can distort star clusters and stellar streams. Just as the Moon's gravity pulls on Earth's oceans, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, and even globular clusters feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, creating long stellar streams or pulling stars away from their orbits. Many of the faint arcs of stars mapped across the sky are the remains of such encounters, clusters in the process of falling apart and galaxies being slowly destroyed. The galaxy does not tear these structures apart all at once. It patiently unravels them, thread by thread, over millions of years. The mass of the Milky Way remains uncertain. You might think we know the mass of our own galaxy, but measuring it is remarkably difficult. Stars and gas make up only a small portion of the total. The rest lies in the vast halo of dark matter, which we cannot observe directly. Estimates vary. Some suggest a mass close to 1 trillion times that of the Sun, while others place it much higher. The uncertainty comes from trying to measure how quickly stars orbit at great distances, a task complicated by limited data and the influence of invisible matter. The Milky Way is our home, but its weight remains a quiet mystery. It may be more massive than Andromeda. For many years, astronomers assumed that the Andromeda galaxy, slightly larger and brighter than the Milky Way, was also more massive. However, more recent measurements suggest that the Milky Way's dark matter halo may be broader and denser than previously believed. If that is true, our galaxy could outweigh Andromeda despite its more modest appearance. This matters not only for comparisons, but also for predictions. When the two galaxies eventually merge, their relative masses will shape the dynamics of the encounter. The Milky Way may appear peaceful, but beneath its calm spiral arms, it may carry more weight than we once imagined. The Magellanic Clouds may be on their first orbit. The Large Magellanic Cloud and the Small Magellanic Cloud, two bright satellite galaxies visible from the southern hemisphere, have long been considered to be orbiting the Milky Way. New evidence suggests that they may be recent arrivals, captured only a short time ago in cosmic terms. Their speed and motion through space suggest that this may be their first close passage. If so, they are not long-term companions, but distant travelers only now falling under the gravitational pull of the Milky Way. Their arrival has disturbed the outer disk and warped the shape of the galaxy. As though the Milky Way were responding to a new gravitational guest, the sky is filled with first encounters. Magellanic Stream is a ribbon of stripped gas. Behind the Magellanic Cloud stretches a vast ribbon of hydrogen gas, a structure known as the Magellanic Stream. It extends across hundreds of thousands of light-years, wrapping through the southern sky in curves and arcs. This stream was torn away by tidal forces as the dwarf galaxies passed near one another and the Milky Way. Invisible in ordinary light, it is revealed at radio wavelengths, a long sigh of motion and loss. The stream may one day fuel the formation of new stars in the Milky Way or settle into the halo like a thread of memory stretching between galaxies. Some gas clouds orbit in polar directions. Not everything in the Milky Way follows the orderly plane of the disk. Some gas clouds and even some stars move along highly tilted orbits, passing above and below the galaxy's main structure. These polar orbits most likely came from past mergers, when dwarf galaxies or scattered clouds were captured at unusual angles. Over time, they continued orbiting along tilted paths like comets circling a planet. These misaligned orbits are records of disruption, visible reminders that the galaxy is not a closed system, but an evolving structure shaped by the unpredictable flow of cosmic history. Gigantic shells of gas surround the sites of past stellar explosions. In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some stretching across hundreds of light-years. These shells are the remains of powerful stellar explosions, episodes in which clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined winds and supernovas carved enormous cavities into interstellar space, pushing gas outward in every direction. Over time, the expansion slows, but the shells remain. They are ghostly bubbles marking where the galaxy once blazed with the force of stellar birth and death. These are the fossils of cosmic fireworks still echoing in the cold. Stars occasionally collide in dense regions. Space is vast, and stars are small. But in the densest regions of the Milky Way, such as the cores of globular clusters, stars can pass close enough to interact and even collide. When they do, the result can be dramatic. There may be a burst of light, the merger of two suns, or the formation of a rare blue straggler star, one that appears younger than its neighbors. These collisions are rare, but they are not impossible. Over billions of years, the most crowded stellar neighborhoods can rearrange themselves through gravity and chance. In these busy cities of stars, time moves differently, and space is never completely empty. Binary stars can be separated by tidal forces. Many stars live in pairs, orbiting one another in a gravitational embrace. But even this bond can be broken. If a binary system passes near the central black hole of the Milky Way or through a dense cluster, tidal forces can disrupt its orbit, throwing one star far away while the other is captured or slowed down. In some cases, one companion is expelled from the galaxy entirely, becoming a wandering star racing through intergalactic space. These stellar separations occur silently in places we rarely see, a quiet tearing apart of ancient partnerships by the indifferent hand of gravity. Some stars escape the galaxy completely. Most stars are gravitationally bound to the Milky Way, but occasionally a star reaches an escape velocity of more than 311 miles per second and is thrown outward, never to return. These hypervelocity stars are rare, but real. Some are believed to be ejected through interactions with the supermassive black hole at the center of the galaxy. Others may be launched by three-body encounters or supernovas in binary systems. Once free, they travel alone into intergalactic space. They become small beacons drifting far beyond the edge of the spiral, carrying the memory of the galaxy outward and becoming solitary pilgrims in the vast darkness between galaxies. Milky Way contains stars from other galaxies. Not every star within the Milky Way was born here. Some may have originated in other galaxies, captured during mergers or thrown into our halo from distant regions of the local group. These intergalactic wanderers often move along unusual orbits far from the disk, tracing paths through the outskirts or halo. They can be identified by their composition or movement, stars that do not quite fit the local patterns. Like cosmic immigrants, they carry stories from other environments, other histories, and other skies. The Milky Way is not a sealed system. It is a living mosaic, slowly stitched together by time and motion. Fountain of gas circulates between the disk and the halo. Above and below the bright disk of the Milky Way, gas rises and falls in a silent loop known as the galactic fountain. Supernovas and stellar winds heat and push material into the halo, where it cools, condenses, and gently rains back down over millions of years. This cycle stirs the interstellar medium, redistributes heavy elements, and helps regulate star formation. It is a quiet breath, a movement of matter between the dense plane and the vast halo. In this way, the galaxy does not only rotate, it circulates. It exhales and inhales, keeping its structure in motion across immense spans of time. The galaxy's dust grains carry organic compounds. Within the clouds of interstellar dust drifting between the stars, scientists have detected complex organic molecules, carbon-based compounds that form essential ingredients for life. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and more. Although they are not alive, they are chemically rich, formed in the atmospheres of dying stars or inside cold clouds shaped by radiation. These tiny grains, carried across light years by galactic winds, settle into the gas that forms stars and planets. Some may have fallen onto the early Earth. The galaxy's dust is not merely debris. It is a cargo of potential floating silently through the darkness. Interstellar clouds can seed solar systems with the ingredients for life. The birthplaces of stars are also the birthplaces of worlds. As planetary systems form from collapsing clouds of gas and dust, they inherit the chemical fingerprints of their parent nebula. If that cloud contains water, carbon compounds, and other building blocks of biology, those ingredients can end up in comets, asteroids, or planets. Some regions of the Milky Way are especially rich in this prebiotic chemistry. We still do not know how common life is, but the conditions that allow it to exist seem to arise naturally. The seeds of life may be scattered everywhere, hidden in the coldest cradles of the galaxy, waiting for a place to grow. Some stars rotate hundreds of times faster than the Sun. Most stars spin, but some do so incredibly quickly, completing a full rotation in only a few hours. These rapid rotators are usually massive, young, and unstable, with equators that bulge outward because of centrifugal force. A few reach such high speeds that they throw off material, forming bright disks around themselves. The Sun rotates once every 25 to 35 days, depending on latitude. But these fast-spinning stars rotate hundreds of times faster, approaching physical limits. Their internal structures and evolutionary paths are different. Their lives may be brief, but while they last, they spin like sirens in the darkness. The galaxy is tilted relative to the ecliptic. From Earth, the Milky Way arches across the night sky like an elegant band of light, but it does not align with the plane of our solar system. The galactic plane, the flat disk where most of the galaxy's stars reside, is tilted by about 60 degrees relative to the ecliptic, the path traced by the Sun and planets. This tilt is why the Milky Way rises at an angle and why its position changes with the seasons. We are part of the galaxy, but our own small system is tilted. A small, slanted vessel floating within a larger, rotating sea of stars. Some stellar remnants are older than the galaxy's disk. Among the faint stars of the halo, astronomers have found white dwarfs, the cooling cores of stars that were once luminous and that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled into place. Their existence points to an earlier era of star formation, a deeper history recorded in the outer halo. They have endured for billions of years, slowly fading and carrying with them the silent remains of a time when the Milky Way was still taking shape. The disk may be bright, but the halo remembers much further back. The most distant stars orbit far beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light-years from the center. These stars move through the galactic halo along slow, wide paths, taking billions of years to complete a single orbit. Many were probably captured from smaller galaxies during past mergers and now float through the farthest reaches like distant sentinels. They are faint, sparse, and widely separated, but they help define the galaxy's size, shape, and gravitational influence. The Milky Way is not only what we can see, it extends deep into the darkness, shaped by the wanderers at its edge. The shape of the Milky Way is uneven in several ways. Although it is often shown as a symmetrical spiral, the Milky Way is subtly unbalanced. One side of the disk is thicker than the other. The spiral arms vary in brightness and length. Even the stellar halo is slightly off-center. These asymmetries most likely arise from gravitational interactions with the Magellanic Clouds, clumps of dark matter, or past mergers. The galaxy is not a perfect pinwheel. It is a living structure marked by pulls and twists, like a dancer whose skirt has been caught by the wind. Its beauty lies in this irregularity, an elegant imbalance sculpted by time. Astronomers map the galaxy using variable stars. Certain stars pulse in brightness at regular intervals, expanding and contracting like slow beats of light. These are variable stars, and some types, such as Cepheids and RR Lyrae stars, have well-known relationships between their brightness and pulsation period. By measuring how long a star takes to brighten and fade, astronomers can determine its true luminosity. By comparing that value with how bright it appears, they can calculate its distance. These stars serve as cosmic measuring rods, helping us map the shape, structure, and scale of the Milky Way. They are lights that measure the darkness, flickering beacons scattered throughout the spiral. The Gaia mission is revolutionizing our understanding of the Milky Way. Launched by the European Space Agency, the Gaia spacecraft is creating the most precise map of the Milky Way ever made. By measuring the positions, movements, and brightness of more than 2 billion stars, Gaia reveals the galaxy's three-dimensional structure and its motion over time. It has uncovered streams from shredded galaxies, mapped the warp of the disk, and traced the sun's orbit in remarkable detail. With every new collection of data, Gaia deepens our understanding, transforming a blurred cloud of stars into a sharp and living map. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars. The galactic plane marks a dense path of stars. If you look up on a dark night far from city lights, you may see a misty river of starlight crossing the sky. That is the galactic plane, the thickest band of the Milky Way's disk. It is not a line, but a depth, a vast flattened region where most of the galaxy's stars reside. Across this plane, stars are densely packed, dust is layered, and star formation is common. From our point of view, we are looking along the length of the galaxy into its richest corridors. This band is not only beautiful, it is the crowded and vibrant heart where most stars live and die. The night sky is brighter toward the galactic center. The core of the Milky Way lies in the direction of the constellation Sagittarius, a rich and brilliant concentration of stars, dust, and invisible mass. From Earth, we cannot see the center itself in visible light because clouds of dust block our view, but the region shines intensely in infrared and radio wavelengths. Even to the naked eye, the area appears more crowded and luminous, filled with the overlapping light of billions of stars. We orbit far from this center, in a quiet suburb of the galactic disk. But when we look inward, we glimpse the crowded city at the heart of the galaxy. See the Milky Way edge on from Earth. Because we live inside it, we cannot look down on the Milky Way from above. Instead, we see it from within as a flat band of stars stretching across the sky, curved only by the horizon. This edge-on view compresses the galaxy into a single arc, making it difficult to understand its full structure from our perspective. It took centuries of observation, cataloging, and mathematical reasoning to recognize the spiral galaxy to which we belong. From Earth, we look through its disk like someone standing in a forest and looking along the line of the trees. We do not see the shape we are part of, only the vastness surrounding us. Galaxy contains far more than we will ever be able to see. Even with our most sensitive instruments, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust. Motion is hidden in silence. Dark matter outweighs luminous stars. Between every star lies emptiness, and within every empty space lies potential. The Milky Way is not only what we see. It is what we suspect, what we infer, and what we long to understand. It contains ancient light, future stars, drifting worlds, and questions that still have no answers. And within that vastness, somehow, we find ourselves, one planet among many, orbiting a quiet star and floating through a story too immense for our eyes. Variable stars make it possible to measure the size of the galaxy. Not all stars shine with the same brightness all the time. Some brighten and dim in an extraordinarily regular rhythm. Among them are Cepheid variables and RR Lyrae stars, whose pulsation cycles are closely connected to their true luminosity. By comparing how bright they should be with how bright they appear from Earth, astronomers can calculate their distance with great precision. These stars made it possible to create some of the first reliable maps of the Milky Way and to discover that the solar system is not located at the center of the galaxy. Each of these pulsations acts like a cosmic beacon, allowing us to measure distances that would otherwise be impossible to cross. Without these natural clocks of light, understanding the true structure of our galactic home would have been far more difficult. The galactic center contains an extremely dense cluster of stars. In the region surrounding the Milky Way's supermassive black hole lies one of the greatest concentrations of stars in the entire galaxy. Millions of them occupy a relatively small volume, moving at extraordinary speeds under the intense gravity of the core. Some complete an orbit around Sagittarius, a star in only a few decades, a speed unimaginable for stars in more distant regions of the disk. Observing these movements made it possible to confirm the existence of the central black hole with great precision and calculate its mass. In this part of the galaxy, the distances between stars are still enormous by human standards, but compared with the rest of the Milky Way, they form an astonishingly crowded neighborhood where gravity controls every path. High-velocity clouds travel through the galactic halo. Far above the Milky Way's disk, immense clouds of hydrogen known as high-velocity clouds move through space. Some travel at hundreds of miles per second and appear to come from both intergalactic space and the galaxy's own internal recycling processes. The origin of all of them is still unknown. Some may be remnants of ancient mergers with dwarf galaxies, while others may be gas falling back after being expelled by stellar explosions. As this material returns to the disk, it can fuel future generations of stars. Although these clouds are nearly invisible to our eyes, radio telescopes reveal enormous streams of gas silently crossing the halo, showing that the galaxy maintains a constant exchange of matter with its surroundings. Open clusters disappear much faster than globular clusters. The Milky Way contains thousands of open clusters, groups of stars born together from the same molecular cloud. However, most do not survive very long in cosmic terms. Close encounters with other stars, the gravitational forces of the galactic disk, and giant gas clouds gradually scatter their members. After a few 100 million years, many of these stellar families no longer exist as recognizable groups. In contrast, globular clusters remain bound for billions of years because of their enormous mass and high density. The galaxy is constantly forming new associations of stars while others quietly disappear, blending into the immense stellar population of the disk. Most of the cold gas is concentrated in a ring around the galactic center. Although the core of the Milky Way is an extremely active region, much of the densest molecular gas gathers in a gigantic ring located several thousand light-years from the center. There, enormous clouds of hydrogen and complex molecules provide the raw material for the birth of new stars. The gravitational forces generated by the central bar help channel some of the gas into this region, where it is compressed and promotes intense periods of star formation. This ring functions as one of the galaxy's main star factories. While the core remains dominated by the influence of the central black hole, an immense reservoir of material surrounds it, continuing to fuel the slow stellar growth of the Milky Way. Some stars travel through the galaxy accompanied by long trails of matter. Stars do not always move cleanly through space. Those that release large amounts of gas through powerful stellar winds can form extensive tails as they pass through the interstellar medium. As a star moves, the expelled gas interacts with the material in its path, creating curved structures similar to the wake left by a ship moving across water. These shapes allow astronomers to determine both the star's speed and the properties of the surrounding interstellar medium. Although they stretch across enormous distances, these tails are extremely faint and can only be observed with telescopes sensitive to different wavelengths. They are silent traces of the constant motion that fills the galaxy. Neutral hydrogen outlines the full shape of the Milky Way. Many regions of our galaxy remain hidden by dust when observed in visible light. However, neutral hydrogen atoms naturally emit a very specific radio signal known as the 21-centimeter line. Thanks to this emission, radio telescopes can see through clouds of dust and reconstruct the distribution of gas throughout the entire galaxy. This method made it possible to discover the extent of the disk, identify spiral arms, and better understand the warp of the outer regions. Much of what we know about the architecture of the Milky Way comes precisely from this faint radio signal that hydrogen constantly emits. Even in areas where no stars are visible, the gas continues to reveal the shape of our galactic home. Massive stars rarely remain where they were born. The heaviest stars in the galaxy live for a very short time compared with stars like the Sun. However, before exploding as supernovas, many quickly leave the regions where they formed. Some are ejected by gravitational interactions within young clusters, while others gain tremendous speed when their companion star explodes first. As a result, astronomers find extremely massive stars traveling alone through the galactic disk, far from any cloud where their birth could have occurred. Tracing their paths makes it possible to reconstruct their history and locate the ancient regions where their lives began. Even the brightest stars in the galaxy can become solitary travelers long before reaching the end of their existence. The galaxy contains enormous regions where almost no stars are born. Although spectacular stellar factories are scattered throughout the Milky Way, there are also extensive areas where the formation of new stars has nearly stopped. In these regions, the gas is too hot, too diffuse, or has been disturbed by earlier explosions that prevent the gravitational collapse needed to begin new generations of stars. Some remain inactive for hundreds of millions of years before receiving fresh gas that restarts the process. In this way, the galaxy alternates between periods of intense activity and periods of relative calm. Not every part of the disk produces stars at the same time. The creation of new suns advances like a changing mosaic that slowly turns on and off across immense spans of time. The Milky Way preserves ancient streams of gas that have not yet been fully absorbed. In addition to streams formed by stars from dwarf galaxies, astronomers have identified enormous structures composed mainly of gas that are still being slowly incorporated into the Milky Way. Some extend across tens of thousands of light-years and represent material that has not yet reached the main disk. These streams serve as future reserves for the galaxy, supplying hydrogen that may eventually become new generations of stars. Studying them helps us understand how galaxies continue growing even after billions of years of evolution. The Milky Way does not preserve the memory of ancient mergers only in its stars. It also holds long, invisible rivers of gas that continue to feed its future in silence. The spiral arms can change shape over time. Although we usually imagine the Milky Way as a permanent spiral, its arms do not keep exactly the same appearance for billions of years. Simulations show that they can strengthen, weaken, split, or even disappear temporarily before reorganizing under the influence of gravity. The distribution of gas, the passage of satellite galaxies, and the collective motion of billions of stars slowly alter their structure. A galaxy observed today could look very different several billion years from now, even if it remains recognizable as a spiral. The great arms crossing the disk are not motionless monuments, but dynamic patterns that continuously evolve along with the entire galaxy. Giant stars shape enormous cavities before they explode. Long before becoming supernovas, the most massive stars release intense winds of particles that sweep away the surrounding gas and dust. Over millions of years, these winds carve enormous bubbles into the interstellar medium that can reach tens or even hundreds of light-years in diameter. When the stellar explosion finally occurs, the shock wave first expands through this previously formed cavity, changing the way energy is distributed throughout the galaxy. Many of the large structures observed in the Milky Way are the combined result of millions of years of stellar winds followed by a single supernova. Even before they die, giant stars begin to transform the galactic landscape around them in profound ways. Some regions of the halo contain gas much hotter than the surface of the Sun. The galactic halo is not made only of ancient stars and dark matter. It also contains enormous amounts of extremely thin gas that reaches temperatures of millions of degrees. Although it is hotter than the surface of the Sun, its density is so low that it emits almost no visible light. It can only be studied through X-ray and ultraviolet observations. This hot gas surrounds much of the galaxy and participates in the cycle through which material rises from the disk and later returns to fuel new generations of stars. Far from being empty space, the halo is an immense, nearly invisible ocean where matter at extreme temperatures circulates around the entire Milky Way. Youngest stars are usually concentrated near the galactic plane. As new stars are born inside the molecular clouds of the disk, they initially remain very close to the galaxy's main plane. However, over hundreds of millions or billions of years, gravitational interactions with other stars, clusters, and giant clouds slowly alter their orbits. Gradually, they begin to rise farther above and below the disk. For this reason, the vertical distribution of stars also reveals their age. Young populations form a thin, bright layer, while older stars are spread through much thicker regions. The geometry of the galaxy itself preserves a silent record of the passage of time across each stellar generation. The galaxy constantly produces complex organic molecules. The cold interstellar clouds of the Milky Way contain more than isolated atoms. Surprisingly, complex molecules also form there through chemical reactions that occur on tiny grains of dust. Astronomers have identified alcohols, aldehydes, aromatic hydrocarbons, and many molecules containing carbon, nitrogen, and oxygen. Some are essential ingredients for prebiotic chemistry. These substances later travel into new regions of star formation, becoming incorporated into future planets, comets, and asteroids. The galaxy acts as a gigantic chemical laboratory where millions of years allow extremely slow reactions to build increasingly complex compounds. Long before a planet is born, part of its future chemistry has already begun forming among the dark clouds of interstellar space. Supernova explosions can trigger chains of stellar birth. When a supernova erupts, its shock wave does more than destroy part of the nearby environment. It can also compress gas clouds located dozens of light years away, beginning new processes of gravitational collapse. If those new stars are massive enough, millions of years later they will produce other supernovas capable of activating even more distant regions. In this way, star formation can gradually spread across different parts of the galactic disk like an extremely slow chain reaction. Rather than occurring completely at random, many episodes of stellar birth are connected through ancient explosions that happened long ago. The death of one generation can quietly become the origin of the next. The galaxy's gas rotates in a more orderly way than many of its stars. Although millions of stars follow orbits altered by gravitational encounters that occurred over billions of years, much of the interstellar gas maintains a far more organized motion around the galactic center. This difference allows astronomers to use hydrogen radio emissions to reconstruct the overall rotation of the disk with remarkable precision. While many stars follow tilted paths, the gas responds more directly to the spiral structure and the dominant gravitational fields. Comparing both types of motion helps reconstruct ancient mergers, stellar migrations, and disturbances experienced by the galaxy. Even when individual stars tell very different stories, the gas continues to trace the collective motion of the entire system. The central regions contain some of the star's richest in heavy elements. Over billions of years, the center of the Milky Way has experienced repeated episodes of star formation and supernova explosions. As a result, much of the available gas has been enriched again and again with elements heavier than helium. Many stars born recently in these regions contain high amounts of iron, silicon, calcium, and other elements forged by earlier generations. In contrast, very ancient halo stars usually preserve far more primitive compositions. This chemical gradient makes it possible to reconstruct how the galaxy evolved at different distances from the core. Each stellar population preserves the memory of the chemical environment that existed at the exact moment of its birth. Galaxy's gravity maintains a delicate balance for billions of years. Billions of stars, enormous gas clouds, clusters, dark matter, and a supermassive black hole constantly interact through gravity. Even so, the Milky Way has preserved a relatively stable structure throughout most of its history. Small disturbances occur continuously, but the whole remains remarkably balanced because of the collective motion of all its components. This balance is never perfect. It slowly adjusts as new stars are born, others disappear, and satellite galaxies slightly alter the distribution of mass. The stability of our galaxy does not come from stillness, but from the dynamic balance between countless forces that have been changing without interruption for billions of years. We are still discovering new structures inside the Milky Way. Even though we live within it, our galaxy continues to hold many secrets. Maps created by space missions and major observatories constantly reveal new stellar streams, hidden clusters, giant molecular clouds, remnants of ancient absorbed galaxies, and complex ripples in the disk. Every improvement in measurement precision makes it possible to uncover details that were once completely invisible. The Milky Way is not a finished puzzle, but a field of research that is always developing. Even as our cosmic home, many aspects of its history, mass, evolution, and deeper structure remain unknown. The better we learn to observe it, the more obvious it becomes that an enormous part of the galaxy still remains to be understood. Giant molecular clouds contain enough material to form millions of stars. Some of the largest molecular clouds in the Milky Way have masses equal to several million suns. Inside them, molecular hydrogen, dust, and an enormous variety of chemical compounds remain at extremely low temperatures, only a few degrees above absolute zero. Despite their immense size, much of these clouds remain stable for long periods before a gravitational disturbance begins the collapse of certain regions. A single giant cloud can give rise to numerous star clusters spread across hundreds of light years. These colossal reservoirs of matter represent one of the most important resources for the galaxy's future, storing the material from which countless generations of stars and planets will be born. The galactic disk contains immense gas filaments hundreds of light years long. In addition to large molecular clouds, the Milky Way contains gigantic filaments of interstellar gas that stretch across hundreds of light years along surprisingly narrow paths. Some contain enough mass to produce thousands of stars, while others appear to connect different active regions of star formation. Astronomers are still studying how these enormous structures originate. Shock waves, magnetic fields, and turbulence in the interstellar medium may all contribute to their formation. Observed in infrared and radio wavelengths, these filaments appear as long, dark arteries running through the galactic disk. Before many stars are born, matter often first organizes itself within these delicate and gigantic structures. Newborn stars release jets that pierce the clouds where they formed. When a protostar begins gathering material from the disk around it, some of that matter does not fall directly onto the star. Instead, it is expelled through powerful bipolar jets emerging from its poles at speeds of hundreds of miles per second. These jets punch through nearby gas clouds, forming spectacular glowing structures known as Herbig-Haro objects. As they advance, they heat and compress the interstellar medium, changing the environment where other stars continue to form. Even before completing their formation, stars already begin altering the galactic landscape around them. Stellar birth is not a quiet process, but an event capable of reshaping its neighborhood for hundreds of thousands of years. The Milky Way contains some of the most luminous stars known. Although most stars have relatively moderate brightness, a few reach extraordinary luminosities. Some blue Hypergents and Wolf-Rayet stars release millions of times more energy than the Sun and produce intense winds capable of throwing enormous amounts of matter into space. Their existence is brief compared with that of smaller stars, but during that short time they completely dominate their surroundings. Their intense radiation ionizes gigantic regions of gas and can either trigger new episodes of star formation or stop them, depending on local conditions. These colossal stars are among the most extreme objects in the entire galaxy, shining intensely before disappearing in spectacular explosions that enrich the interstellar medium. Neutron stars can travel through the galaxy at extraordinary speeds. When a massive star explodes as a supernova, the explosion does not always occur with perfect symmetry. If there is even a slight imbalance, the neutron star left behind can receive an enormous kick that launches it at speeds of hundreds or even more than 621 miles per second. These compact objects travel across the galactic disk for millions of years, quickly moving away from the places where they were born. Some eventually leave the galaxy's main plane and spend much of their existence traveling through the halo. Despite measuring only a few dozen miles across, they contain more mass than the Sun and become some of the fastest travelers in the entire Milky Way. Star-forming regions also produce brown dwarfs. Not all the material collapsing inside a molecular cloud manages to form a true star. In many cases, the fragments do not contain enough mass to begin stable hydrogen fusion. The result is a brown dwarf, an object between a giant planet and a star. Brown dwarfs release heat for billions of years as they slowly cool, but they never achieve the permanent brightness of a sun. The Milky Way probably contains billions of them scattered throughout the disk and halo. Many remain hidden because of their faintness and can only be observed with highly sensitive infrared telescopes. They form a quiet population born from the same processes as stars, but destined to follow a completely different path. Interstellar dust protects the chemistry of future planetary generations. The tiny grains of dust floating between the stars do far more than simply block light. Atoms and molecules attach to their surfaces and slowly react, forming increasingly complex compounds. These grains also act as shields that protect many molecules from the intense ultraviolet radiation present throughout the galaxy. When new stars and planets begin to form, some of this enriched dust becomes incorporated into protoplanetary disks, where it continues to evolve chemically. In this way, materials processed for millions of years in interstellar space eventually become part of future worlds. Much of the chemical richness of planetary systems began long before the birth of their own stars. Young stars can remain hidden throughout much of their birth. Even while a protostar is already gathering mass and heating rapidly, it can remain completely invisible in visible light for hundreds of thousands of years. This happens because it is still surrounded by a thick cloud of dust and gas that absorbs nearly all the radiation it emits. Only infrared and radio telescopes can penetrate this cocoon and observe the earliest stages of stellar birth. When powerful winds and radiation finally clear away the surrounding material, the new star appears, shining through the cloud that gave rise to it. Many of the stars visible today spent much of their infancy completely hidden from the outside universe, growing silently behind a thick veil of interstellar dust. Stellar orbits can change slowly over billions of years. Stars do not follow exactly the same path around the galactic center forever. Across immense spans of time, gravitational interactions with spiral arms, star clusters, giant molecular clouds, and other concentrations of mass gradually alter their orbits. This phenomenon, known as radial migration, allows many stars to end up far from where they were born without being violently ejected. As a result, the stellar neighborhood currently surrounding the Sun probably contains stars that came from very different regions of the galaxy. The Milky Way slowly mixes its stellar populations, spreading its history throughout the entire disk. Complete history of the Milky Way is still written among billions of stars. Every star preserves information about the time and place of its birth. Its chemical composition, speed, orbit, and age serve as pieces of an immense puzzle that astronomers are still reconstructing. Thanks to space missions capable of measuring the motion of millions of stars with extraordinary precision, new evidence of ancient mergers, periods of star formation, and changes in galactic structure appears every year. The Milky Way does not preserve its past in documents or monuments. It keeps it distributed among countless suns that continue moving slowly through space. Understanding the history of our galaxy essentially means learning to read the memory written in the light of each of its stars. The Milky Way contains vast regions where hydrogen is completely ionized. Not all interstellar gas remains cold and dark. Near very hot young stars, there are enormous bubbles where intense ultraviolet radiation has stripped electrons from hydrogen atoms, forming what astronomers call regions of ionized hydrogen. These gigantic clouds glow with reddish colors when observed at certain wavelengths and mark some of the most active regions of star formation in the galaxy. New clusters continue to form there while radiation from recently formed stars constantly changes the surrounding environment. These regions represent some of the most dynamic landscapes in the Milky Way, where the light of young suns transforms the gas that may one day give rise to new generations of stars. Smallest stars will live long after the brightest ones disappear. The vast majority of stars in the Milky Way are not luminous giants like those we often imagine, but modest, low-mass red dwarfs. These stars consume their fuel with extraordinary efficiency and can remain active for hundreds of billions or even trillions of years, far longer than the current age of the universe. While the most massive stars live for only a few million years before exploding, red dwarfs evolve slowly, shining with moderate intensity for extraordinarily long periods. When most of the galaxy's bright stars have disappeared, countless red dwarfs will continue quietly illuminating the galactic disk, extending the stellar life of the Milky Way into an unimaginably distant future. Dark clouds can completely hide enormous regions of the galaxy. Some concentrations of interstellar dust are so dense that they block nearly all visible light coming from the stars behind them. These structures, known as dark nebulas, appear as enormous black silhouettes against the glow of the galactic background. However, intense activity is often hidden behind that apparent emptiness. Many contain protostars, protoplanetary disks, and dense cores where new stellar systems continue to form. Only infrared or radio observations can penetrate these curtains of dust and reveal what they contain. What our eyes interpret as absolute darkness is often simply a veil concealing some of the most active processes in the entire galaxy. Red giant stars slowly enrich the interstellar medium. When stars similar to the Sun reach the final stages of their evolution, they expand enormously and begin losing their outer layers through gentle stellar winds. Over hundreds of thousands of years, they release large amounts of carbon, nitrogen, and other elements created within their interiors. This material slowly mixes with the galaxy's gas and eventually becomes part of future generations of stars, planets, and even possible forms of life. Unlike the violent explosions of supernovas, this enrichment occurs gradually and continuously. Millions of red giants scattered throughout the Milky Way quietly help renew the chemical composition of the interstellar medium, becoming one of the main sources of elements essential to galactic evolution. The speed of sound varies enormously between different regions of the galaxy. In the vacuum of space, we often think that sound cannot travel, and that is correct in regions that are nearly empty. However, inside the Milky Way's gas clouds, there are enough particles to transmit pressure waves. The speed at which these waves move depends on the temperature and density of the gas. In some cold clouds, it reaches only a few hundred feet per second, while in the extremely hot gas of the halo, it can greatly exceed 62 miles per second. These differences affect the movement of shock waves produced by supernovas and the evolution of star-forming regions. Even the behavior of galactic gas depends on properties as fundamental as the speed at which its smallest disturbances travel. The galaxy contains regions where dozens of stars are born almost simultaneously. In certain areas of large molecular clouds, gravitational collapse does not occur in isolation. A single disturbance can simultaneously trigger the formation of dozens or even hundreds of protostars within a relatively small volume. The result is young star clusters in which nearly every star has a very similar age. These true cosmic incubators allow scientists to study how an entire group of stars evolves from its earliest stages. Some will remain bound together for millions of years, while others will begin to scatter shortly after birth. The Milky Way does not always produce stars one at a time. On many occasions, it creates them in genuine waves that illuminate entire regions of the galactic disk. The gravity of giant clouds can alter the motion of nearby stars. Enormous molecular clouds do more than serve as factories for new stars. Because of their tremendous mass, they also exert a significant gravitational influence on stars that pass near them. Over millions of years, these encounters slowly modify stellar orbits, slightly changing their speeds and directions. Although each individual change is small, the accumulated effect eventually contributes to the migration of many stars across the galactic disk. These gigantic reserves of gas therefore participate not only in the birth of new stellar generations, but also in the gradual reorganization of existing ones. Even before becoming stars, these immense clouds are already shaping the overall dynamics of the galaxy. Some nebulas preserve the imprint of ancient explosions that occurred millions of years ago. When several massive stars are born close together, their winds and later supernovas can create enormous gas complexes whose structures remain visible for millions of years. These regions contain cavities, filaments, and expanding shells that reveal a long history of successive explosions. By analyzing their shape, chemical composition, and rate of expansion, astronomers reconstruct events that occurred long before humanity existed. Many present-day nebulas are genuine fossil archives in which the stellar activity of ancient ages remains recorded. The galaxy preserves the memory of its most energetic episodes in gigantic gas structures that continue expanding slowly through space. The hottest stars emit much of their energy outside visible light. Although some stars appear extremely bright to our eyes, most of the energy produced by the hottest stars in the Milky Way is emitted as ultraviolet radiation. This intense radiation is essential for transforming interstellar gas, ionizing enormous clouds, and triggering many physical processes throughout the galaxy. However, Earth's atmosphere absorbs nearly all of this radiation, making space telescopes necessary for studying it directly. These observations have revealed that many apparently quiet regions of the galactic disk are being intensely illuminated by energy that is invisible to human vision. The galaxy's true energetic appearance is very different from what our eyes perceive. The Milky Way continues to reveal new secrets with every generation of telescopes. Each technological advance allows us to observe the galaxy with a level of precision that once seemed impossible. New radio telescopes, infrared observatories, space telescopes, and three-dimensional maps of millions of stars continue uncovering unknown structures, refining distances, and revealing physical processes that had remained hidden. Many ideas accepted for decades have had to be adjusted as more precise data has appeared. The Milky Way is not only the place where we live, but also one of the most complex scientific laboratories we know. The more deeply we learn to observe our own galactic home, the more clearly we understand that we are still taking only the first steps toward understanding all the richness and complexity it contains. The most active regions of star formation often illuminate enormous emission nebulas. When groups of very young stars begin to shine, their intense ultraviolet radiation transforms the surrounding hydrogen into an immense glow visible across hundreds of light years. These emission nebulas are among the most spectacular structures in the Milky Way and make it easy to identify regions where new generations of stars are still being born. As time passes, stellar winds and radiation slowly disperse the gas, changing the appearance of the region until the young stars are finally exposed. Many of the great nebulas observed by telescopes represent only a brief moment within a process that will continue transforming the galactic landscape for millions of years. Some stars have magnetic fields millions of times stronger than Earth's. Although every star generates a magnetic field to some degree, a small group develops extraordinary intensities. In certain cases, especially among neutron stars known as magnetars, these fields reach such extreme levels that they profoundly alter the matter and radiation around them. Even ordinary stars can possess enough magnetism to affect their stellar winds, rotation, and the distribution of surrounding material. Magnetism is a silent force that continuously influences the evolution of many objects throughout the galaxy. Far beyond gravity and light, invisible magnetic lines constantly take part in the complex dynamics of the Milky Way. Young stars often retain disks where planetary material is still forming. After a star is born, some of the gas and dust that was not incorporated into it remains in orbit, forming a protoplanetary disk. Within these structures, tiny particles begin joining together through countless collisions, gradually growing into larger bodies. Over millions of years, these disks evolve as planetesimals, protoplanets, and eventually complete planetary systems appear. Modern telescopes have photographed many of these disks, revealing rings, gaps, and spirals where new worlds are probably already forming. The Milky Way contains countless systems at different stages of this process, showing that the construction of planets is constantly taking place in many regions of the galaxy. Interstellar gas can remain stable for millions of years before collapsing. Not every molecular cloud immediately begins forming stars. Many remain in a delicate balance in which gravity tries to compress the material while thermal pressure, magnetic fields, and internal turbulence resist the collapse. This balance can continue for millions of years until an outside event, such as the passage of a shock wave or an interaction with another cloud, breaks the stability and triggers stellar birth. For this reason, the presence of abundant gas does not guarantee that a region will immediately produce stars. Much of the galaxy's raw material remains silently waiting for the right conditions to begin a process that will completely change its destiny. The orbits of globular clusters allow scientists to study the distribution of galactic mass. Ancient globular clusters follow paths that carry them far above and below the Milky Way's main disk. By carefully tracking their movements, astronomers can calculate how gravity is distributed across enormous distances from the galactic center. These clusters act as natural probes moving through regions where very few visible stars exist. They have helped produce better estimates of the extent of the dark matter halo and explain how gravity behaves in the galaxy's most distant regions. Each of these ancient swarms of stars not only preserves information about the past, but also helps map the invisible architecture that supports the entire Milky Way. The composition of dust changes as it travels through the galaxy. The tiny solid grains found between the stars do not remain unchanged throughout their existence. As they move through the interstellar medium, they can grow by gathering new layers of ice and molecules, break apart after collisions, or be eroded by the intense radiation of nearby stars. Each of these processes alters their physical and chemical properties, changing the way they absorb, reflect, and emit light. As a result, dust observed in different regions of the Milky Way has different characteristics depending on the environment in which it evolved. These small grains play an essential role in the formation of complex molecules and the birth of new stars, making them one of the most dynamic components of the galactic ecosystem. Massive stars usually form in the densest cores of molecular clouds. Although large gas clouds contain enormous amounts of material, only certain regions reach densities high enough to produce the most massive stars in the galaxy. These dense cores concentrate tremendous amounts of mass within relatively small volumes, allowing gravity to act with great intensity. Stars dozens of times more massive than the Sun can form there, rapidly transforming their surroundings through radiation, stellar winds, and later supernovas. The formation of these giants is one of the most important processes in galactic evolution because they enrich the interstellar medium with new elements and regulate the birth of future stellar generations through their powerful energy. Stars of the galaxy are not all born with the same rotational speed. From their earliest moments, each star acquires a rate of rotation determined by the amount of angular momentum inherited from the cloud that formed it. Some complete a rotation in only a few hours, while others require several months. Over time, stellar winds and magnetic fields gradually change that speed, especially slowing stars similar to the Sun. Studying how rotation changes makes it possible to estimate the age of many stars through a technique known as gyrochronology. Even the movement of a star around its own axis preserves information about its history. Rotation is another part of the complex record each star carries about its evolution within the Milky Way. Shock waves can travel enormous distances before disappearing. When a supernova explodes or a group of massive stars releases powerful winds, the resulting pressure waves begin expanding through the interstellar medium. Although they gradually lose energy, they can travel dozens or even hundreds of light years before completely fading away. Along the way, they compress gas, shape filaments, trigger new gravitational collapses, and alter the chemical and physical structure of the regions they cross. A single stellar explosion can influence an immense volume of the galaxy for millions of years. In this way, highly localized events can eventually affect the evolution of regions located far from where they occurred. Every new space mission transforms our view of the Milky Way. Over recent decades, increasingly precise satellites and telescopes have revolutionized our knowledge of the galaxy. Observatories capable of measuring positions, speeds, chemical compositions, and distances with unprecedented accuracy continue revealing details that were previously impossible to detect. These advances lead to the discovery of new stellar streams, hidden clusters, gas structures, and patterns of motion that require galactic models to be constantly improved. The history of the Milky Way continues to be written with every new generation of instruments. Even though we live inside it, we are still creating the first truly detailed map of our own cosmic home, a task that will probably continue for many more decades. Binary stars are far more common than they appear. Although we often imagine stars as solitary objects, a large fraction of them belong to binary or multiple star systems. Two stars can orbit a common center of gravity for millions or even billions of years, separated by vastly different distances depending on the system. Some orbit so close together that they continuously exchange material, while others remain separated by hundreds of times the distance between Earth and the Sun. These interactions profoundly affect their evolution, sometimes leading to supernova explosions, unusual white dwarfs, or intense X-ray emissions. The Milky Way is not populated only by isolated suns. A large portion of its stars shares its existence with a gravitational companion, forming delicate cosmic dances that endure for immense periods of time. Hottest stars create enormous ionization fronts that move through space. When a very massive star begins emitting intense ultraviolet radiation, the boundary between neutral gas and ionized gas slowly moves outward. This boundary, known as an ionization front, can travel across dozens of light-years as it transforms the interstellar medium. As it advances, it changes the temperature, pressure, and chemistry of the surrounding gas, encouraging the formation of new stars in some places while making it more difficult in others. These fronts continuously reshape the appearance of nebulas and remodel vast regions of the galactic disk. The light from a single star can alter the fate of enormous amounts of matter far beyond the place where it was born. The galaxy contains enormous reservoirs of hydrogen that are not yet taking part in star formation. Although new stars are born each year in different parts of the Milky Way, much of the available hydrogen remains spread throughout enormous clouds that are too diffuse to collapse under gravity. These reservoirs can remain virtually unchanged for hundreds of millions of years, waiting for the right conditions to become concentrated and begin a new episode of star formation. Shock waves, gravitational interactions, and the movement of gas can slowly reorganize this material until it becomes future molecular clouds. In this way, the galaxy maintains an immense storehouse of raw material, ensuring that stars can continue forming for a very long time, even if the current rate of star formation continues to decline gradually. Ancient stars help reconstruct the galaxy's historical motion. Every star preserves the speed and direction it has acquired throughout its evolution. By measuring millions of these motions with great precision, astronomers can reconstruct ancient mergers, gravitational disturbances, and shifts in the galactic disk that occurred billions of years ago. Present-day trajectories serve as dynamic fossils that reveal events long since vanished. Even small groups of stars that now appear scattered can reveal that they once belonged to the same dwarf galaxy absorbed by the Milky Way. The memory of the past is preserved not only in the chemical composition of stars, but also in the way they continue moving through space. Radiation pressure also shapes the evolution of the galaxy. Gravity is usually considered the dominant force within the Milky Way, but the light emitted by stars also exerts a small pressure on interstellar gas and dust. In regions where many massive stars are forming, this pressure can slowly push enormous amounts of material, clearing cavities, displacing dust, and changing the distribution of gas. Although the effect is much weaker than gravity, over millions of years, it actively contributes to transforming the interstellar medium. Light does more than illuminate the galaxy. It also pushes, rearranges, and shapes part of the material that will one day form new generations of stars. Most massive stars live such short lives that they barely complete a galactic orbit. Some of the largest stars ever known consume their fuel at an extraordinary rate and explode only a few million years after they are born. That span is so brief that many do not even travel a small fraction of their orbit around the center of the Milky Way before disappearing. While the Sun will need hundreds of millions of years to complete a single orbit around the galaxy, these colossal stars are born, brilliantly illuminate their surroundings, and die long before moving a significant distance across the galactic disk. Their existence is little more than a brief flash within the galaxy's slow motion, yet during that short time, they profoundly transform the environment around them. Interstellar gas forms swirling currents driven by the galaxy's rotation. As the Milky Way rotates, differences in speed between one region and another generate enormous shearing motions within the interstellar gas. These motions create swirling currents and turbulent structures that slowly mix material from different parts of the galactic disk. As a result, elements forged by ancient generations of stars can gradually spread into regions far from where they were created. This chemical mixing helps future stars form with similar compositions across broad areas of the galaxy. The galaxy's rotation does more than move stars. It also slowly stirs the immense ocean of gas from which future stellar systems will emerge. Newly formed stars often remain surrounded by remnants of their birth clouds. Even after nuclear fusion begins, many young stars continue to be surrounded by some of the gas and dust from which they formed. This leftover material can create envelopes, disks, and small nebulas that remain visible for hundreds of thousands of years before completely dispersing. During that time, the star's intense radiation begins carving cavities, pillars, and filaments into the original cloud. These natural sculptures reveal in remarkable detail the interaction between starlight and the interstellar medium. Many of the most spectacular images captured by space telescopes come from these earliest stages, when a star still retains part of the environment that gave it life. The oldest stars continue enriching the galaxy even at the end of their lives. As they age, many stars gradually release material through pulsations and increasingly powerful stellar winds. This process can continue for hundreds of thousands of years before the star finally sheds its outer layers. The released elements are slowly incorporated into the interstellar medium, supplying the chemistry of future generations of stars and planets. Although each individual loss may seem small, the enormous number of aging stars spread throughout the Milky Way makes this mechanism a constant source of galactic renewal. Even during their final moments, stars continue quietly, contributing to the evolution of the entire galactic system. Every discovery about the Milky Way tends to raise new questions. The more closely we observe our galaxy, the more obvious it becomes that much remains to be understood. New maps reveal unexpected structures, more precise measurements revise earlier estimates, and increasingly sophisticated simulations uncover processes we are only beginning to understand. Topics such as the exact distribution of dark matter, the origin of certain stellar streams, the evolution of the central bar, and the complete history of the earliest galactic mergers remain subjects of active research. The Milky Way is not a solved problem, but one of the greatest challenges in modern astronomy. Our cosmic home still holds countless secrets, waiting to be discovered by future generations of observers and explorers of the universe. Milky Way contains regions where gas rotates in a different direction from the main disk. Although most of the galaxy's gas follows the overall pattern of rotation, astronomers have identified structures in which certain gas clouds move along different orientations. In many cases, these streams represent material captured from dwarf galaxies or gas that fell from the halo after following complex paths. As they merge with the main disk, they create regions where different streams interact slowly over millions of years. Studying these motions helps reconstruct ancient episodes of accretion and explains how the galaxy continues gathering matter from its surroundings. Even within a system as organized as the Milky Way, there are still currents that preserve the memory of very different origins. The galaxy contains immense, nearly empty cavities carved by generations of stars. In some regions of the galactic disk, astronomers have discovered enormous areas where the density of gas is surprisingly low. These cavities were created by the combined effects of stellar winds and multiple supernovas that occurred within ancient massive star clusters. Over time, the explosions pushed much of the material outward, leaving enormous, relatively clear spaces surrounded by dense walls of gas. Many of these cavities span hundreds of light years and continue expanding slowly. Far from being inactive regions, they represent the accumulated result of millions of years of intense stellar activity that profoundly reshaped the structure of the interstellar medium. Molecular hydrogen is surprisingly difficult to observe directly. Although it makes up most of the material from which stars are born, molecular hydrogen emits very little detectable radiation under the cold conditions of interstellar space. For this reason, astronomers usually study other molecules present in small amounts, especially carbon monoxide, whose emissions are much easier to detect with radio telescopes. By analyzing that signal, they can estimate the distribution of hidden hydrogen and reconstruct the locations of the great molecular clouds scattered throughout the galaxy. Much of what we know about the Milky Way's stellar factories comes from this ingenious indirect method, which reveals immense reservoirs of gas that remain invisible to conventional observation. Stars can slowly change the chemical composition of an entire galactic region. Each stellar generation transforms some of the original hydrogen and helium into heavier elements through nuclear reactions. When those stars release material into space, they enrich the surrounding interstellar medium. Over millions of years, new generations are born from that enriched gas, gradually increasing the abundance of elements such as carbon, oxygen, silicon, iron, and calcium. This process occurs again and again in different regions of the galactic disk, creating continuous chemical evolution. The Milky Way does not always maintain the same composition. Slowly, generation after generation, its stars transform the elemental content of the entire galaxy through a permanent cycle of birth, evolution, and renewal. Some stars produce intense winds throughout much of their stable lives. A star does not need to reach the end of its existence before it begins releasing matter. Many very hot stars generate powerful winds driven by the pressure of their own radiation from relatively early stages of their evolution. These streams of particles can carry enormous amounts of material into space at speeds of thousands of miles per second. Over millions of years, these winds sculpt the interstellar medium, contribute to galactic chemistry, and alter the star's later evolution by gradually reducing its mass. Even during their apparent stability, some stars actively participate in the continuous transformation of the environment around them. The Milky Way contains many overlapping generations of stars. When we observe any region of the sky, the visible stars rarely belong to a single period of formation. In the same area, newly born stars may coexist with others that are billions of years old and some that are approaching the end of their lives. They are all mixed together because of slow orbital motion and stellar migration across immense spans of time. As a result, the galaxy functions as a vast archive where different generations coexist simultaneously. Every star represents a different chapter in galactic evolution. Looking at the night sky is like observing millions of stories unfolding at the same time, written during very different periods in the long life of the Milky Way. Stellar explosions help keep part of the interstellar medium hot. The space between stars contains gas at extremely different temperatures. A significant portion remains hot because of the energy continuously released by supernovas and stellar winds. These sources inject heat and motion into the interstellar medium, preventing large regions from immediately collapsing under gravity. The balance between heating and cooling determines when a cloud can become a new star factory. The evolution of the galaxy depends greatly on this delicate energy balance. Without the constant contribution of its most energetic stars, interstellar gas would behave very differently, and star formation would proceed at a very different rate. Open clusters make it possible to study stellar evolution with great precision. Because all the stars in an open cluster were born at nearly the same time from the same molecular cloud, they are exceptional natural laboratories for understanding stellar evolution. Although they have different masses, they share very similar ages and chemical compositions. By comparing their brightness and temperature, astronomers can directly observe how the appearance of stars changes as they age. Each cluster represents a snapshot of a specific stage of stellar development. By analyzing many clusters of different ages, it is possible to reconstruct much of the evolutionary cycle of the stars that populate the Milky Way without waiting millions of years to observe those changes directly. The gravity of the disk keeps much of the galactic gas confined. Despite stellar explosions, powerful winds, and the energy continuously released by billions of stars, most of the Milky Way's gas remains concentrated near the plane of the disk. The combined mass of stars, dark matter, and gas creates enough gravitational attraction to prevent most of the material from escaping into intergalactic space. Only a small fraction reaches the halo before cooling and slowly returning. This balance between the energy expelled by stars and galactic gravity keeps the continuous cycle of matter recycling active. The galaxy retains much of the material needed to continue forming new generations of stars far into the future. And so our journey through the Milky Way comes to an end. Although we have explored some of its most astonishing secrets, our galaxy still holds countless mysteries waiting to be discovered. As the stars continue their slow journey through the cosmos, we are only beginning to understand the immense home we inhabit. Perhaps the next time you look up at the night sky, you will do so knowing that every tiny point of light is part of a story far greater than we ever imagined.
If you enjoyed the video, don't forget to like it and share it with your friends. Subscribe so you don't miss more interesting content. Leave your comments and click on any of these videos. See you next time.